Ian, I don't know if you knew this about me, but I'm a Texan.
What? You? From Texas? I had no idea.
Yeah, I drive my husband crazy talking about it. For my 30th birthday, I had a fully Texan birthday where I made everyone wear pearl snaps and cowboy hats, and we only had queso and Shiner beer, and I refused to play any music that wasn't from Texas. Except Asleep at the Wheel, they always get a pass.
Wow. Sounds fun. Thanks for the invitation.
I'm pretty sure you were out of town. I refuse to be blamed for this. But the reason that I'm bringing this up is although I've left Texas behind for the Windy City, I still get regular updates from my family who live in Central Texas. And that includes hearing about the absolutely insane weather events.
Oh, yeah. Wasn't there something about the state losing power during a cold snap?
So nearly 3 million customers without power this morning.
Rolling outages, power outages across the state.
That leaves up to 2 million Texans without guaranteed warmth for what looks to be an incredibly frigid night ahead.
Oh, yes. So that happened. And then, of course, there's like the multiple hurricanes that hammer the coast over the years, including that recent one, the deadly Hurricane Harvey.
Hurricane Harvey, state of emergency.
We're not measuring in inches of rain, we're measuring in feet of rain.
Harvey, the most powerful hurricane to hit this state since John F. Kennedy was president, is now a massive tropical storm.
So would you be surprised to learn that one of the first questions I asked today's guest was about where I should live to avoid the increasingly dangerous storms caused by climate change? Based on your research, when you've thought about these kind of rare, bad storms and rare events, have you thought about like where's the best place to live in the United States if you want to avoid all the bad weather from climate change?
I don't know, because I would have said I would have said somewhere like Colorado or Western United States, but then they're all being affected by wildfires. Here on the East Coast, we're worried by hurricanes, and I guess in a place like Chicago, you have extreme winters and sometimes extreme lake effects there. I would have thought that going further west was better, but no, they have wildfires there, so maybe there isn't any safe place anymore.
Actually, I used to think about this growing up. I remember thinking that living in Denver was perfect because we didn't have hurricanes or floods or tornadoes. It is a desert, though, so, not a lot of water. So I thought living in Chicago is good because there is water here and you don't have to deal with the other things. But then you look at, the erosion of the lakefront, and apparently it also affects the sewage system. Are we going to be talking about how to escape climate change? Because, seems like you can't.
You're right. We are talking about climate change. But to be more specific, today we're speaking with a professor of statistics and biostatistics at the University of North Carolina, Chapel Hill. His name is Richard Smith, and he's going to explain how we can predict rare weather events, kind of like Hurricane Harvey, and why predicting rare events is hard, because they happen, well, rarely, but often with devastating consequences.
I'm Ian Martin.
And I'm Sadie Witkowski.
And this podcast is brought to you by Existential Dread.
Okay, I like to think this doesn't have to be depressing, but we are talking about climate change and rare weather events like the poorly named 100-year flood idea.
Okay, fine. You're listening to Carry the Two, a podcast from the Institute for Mathematical and Statistical Innovation, aka IMSI.
This is the podcast where my co-host Ian and I talk about all the ways we use mathematical and statistical research to understand the world around us.
Well, you talk. I listen and sometimes respond. My math knowledge, as you know, is limited to high school, and I never even took a statistics class.
Hey, my background as a cognitive neuroscientist means it's been all stats for me. But I knew when I started at IMSI, I really wanted a partner in crime for this podcast who's really super curious about math research, or in the case of this week, focused on the statistical side.
I literally just said I never took a statistics class.
You never did the thing where you had to pick colored balls out of a hat?
No, what's that?
Okay, that's like the stereotypical example from high school statistics classes, but it's really a strong example of understanding probability and statistics that I still tend to use today. And for listeners who might not remember, we're talking about the standard class example where if there are 5 red balls and 15 blue balls in the hat, you can easily see how you have a 5 in 20 or 25% chance of picking a red ball.
So basically, it's just like a simple example that gives you a sense for how often a particular thing might happen.
Yeah, exactly. But when it comes to rare events, most people don't connect this idea from statistics to the idea of a 100-year flood or a 500-year flood.
Yeah, you mentioned that earlier. Is that like a common term?
You hear it pretty commonly when listening to reporting on flooding, especially if you live in Houston. But I think it can be a confusing term for people sometimes.
People get the idea, which is really rather misleading, which is that the 100-year flood is something that occurs exactly once every 100 years. Okay, so that, and then of course you get 200-year floods, sometimes even in consecutive years, and people are like, well, what on earth went wrong there? That was supposed to only happen once in 100 years. So what the 100-year flood really means is what you're looking at, the level, whether you're talking about the water. With floods, it's usually about the height of a river or the height of the sea. What's the height that would occur in any one year with probability 1 in 100? So even if that was literally true, that doesn't actually rule out the possibility you might get the same height 2 years running.
So having one 100-year flood doesn't preclude you from experiencing another one the very next year.
Oh, okay. So you have a 1 in 100 chance of getting that much rain, not that it only happens once every 100 years, like flipping a coin and getting heads twice in a row. Just because you have a 50-50 shot doesn't mean the previous flip affects the next one.
You nailed it. I think people hear the term 100-year flood and assume that once it happens, the chances of it happening again go down. But you have that 1 in 100 chance every single year. And sometimes, like you mentioned, you just get heads twice in a row, so to speak.
Okay, I get the concept, but I guess I have 2 main questions. First of all, how do we even know what a 100-year flood will look like? Like, how are we making these predictions? And secondly, how much can we trust the predictions? Doesn't climate change mean that these rates might be changing?
This is where we get to one of Richard's subfield specialties, extreme value theory.
So the idea is that extreme value theory is a tool that people use in analyzing experiments that are dependent on the most extreme values, and strength of materials is an example because it tends to be the weakest members of an ensemble of whatever that determine the strength of the system.
So basically, when he says weakest member of an ensemble, does he mean like the weakest link in a chain?
Yeah, I think that's the best comparison.
And then extreme value theory is a way of looking at those 1 in a million cases?
Yeah, and it's all based on understanding the underlying statistical distribution.
I distribute grades. I think I understand.
Okay, but just in case, let's back up for a second and explain what a normal distribution is so that all of our listeners are on board.
That's probably a good idea. I mean, I have a vague sense of what it is, but I can always use a refresher.
So when we talk about a normal distribution, you can think of the image of a bell curve. It's called that because, well, it sort of looks like a bell, where the center is the tallest section and then the edges to the far left and right taper off into these skinny tails.
Oh, sort of like a Pac-Man ghost, but the edges maybe don't drop straight down.
Yeah, and that shape then can be broken into vertical sections or chunks, which then give you what are called the standard deviations. So most data points are clustered around the center, which is the average or the mean, and then those deviations go out into the tails.
And that's because, like, most people are average. I mean, like, not us, but most people.
Yeah, so in a normal distribution, like we see for height or driving ability, something like that, we're all mostly average and center around the mean. And then we have our outliers as the ones on the far edges of the distribution. So if we were looking at height, then these are our extremely tall people on one end and the extremely short folks on the other.
Okay, so how does this apply to extreme value theory?
Well, rather than looking at people in a population, we can also look at how frequently major weather events tend to happen. But it turns out that these weather events aren't distributed in a normal distribution. The tails at either end are actually fatter than you'd see in a normal distribution, meaning that those rare events are actually less rare than you'd expect. Although I have experience working with normal distributions from my time as a neuroscientist, I didn't spend much time thinking about the tails of the distribution. So I had to ask Richard whether it's harder to predict rare weather events because you have less data on them or for other reasons.
So usually with this kind of analysis, we don't use normal distributions because with normal distributions, the tails actually do decrease very quickly. And that's a mistake sometimes people have made. They've assumed that normal distributions occur. And I mean, with a normal distribution, the probability, say you're 3 standard deviations away from the mean is I can't remember the exact number now, it's about 3 parts in 1,000. And a lot of time people realize that the true probability is much higher than that. And what extreme value distributions try to do is to come up with alternative types of distribution that more realistically reflect what's going on in the tails. So maybe with a 3 standard deviation departure, maybe it's not 1 in 1,000, maybe it's 1 in 100 or even more than 1 in 100. But to get to the other part of your question, well, yes, it's true that we don't have a lot of observations of these very extreme events. And that does affect how well we can fit these distributions. In recent years, people have come up with alternative methods of fitting them. For instance, you can expect that, say weather stations in the same region probably have rather similar distributions. And people have come up with methods of fitting the data that take account of that. So you can borrow strength from one location to understand better what is going on at another location.
Okay, I get what Richard means. So extreme value theory is taking the tail events,
The outliers.
and is trying to make predictions about those.
Exactly. It's trying to get a better sense of what exactly is happening at those tail ends. Of course, part of the problem with predicting a rare weather event is, well, it's rare. So you wouldn't have as many previous events to compare it against, making it harder to make those kinds of predictions. Let's actually go back to that 100-year flood idea.
So essentially, the way people characterize a 100-year return level or any type of return level is you take the data might be, say, the annual maximum rainfall or river height, whatever it is you're measuring at a particular location. Let's say you can measure that. In many places we have at least 50 or 60 years of data, sometimes much more than that. And essentially what it comes down to is taking that data and fitting a distribution to it. And it turns out there are certain particular classes of probability distributions that are appropriate to this that are called the extreme value distributions. And essentially what the method comes down to, or at least the simple form of the method, I mean, there's many ways it's been generalized in recent years, but the basic idea is you take the data that you have and you fit one of these distributions to the data, and then you can read off the 100-year level or the 500-year level or whatever it is you need from that.
So if you have decent data going in, you can use extreme value distributions to give you a sense for these rare events by fitting it into a modified bell curve. That's pretty cool.
Yeah, of course, we're assuming that the historical frequency of these events can help us predict what'll actually happen in the future. But what if, I don't know, say we were adding a bunch of greenhouse gases to the atmosphere and changing the underlying distribution?
I'd say, hey, you, stop doing that.
And while I don't have control of all the power plants pushing all these greenhouse gases out, I do have control of this podcast. So let's take a short break, and then we'll get into the math of modeling that climate change. If you're getting a lot out of the important research shared on our show, there's another University of Chicago Podcast Network show that you should check out. It's called Not Another Politics Podcast. Not Another Politics podcast provides a fresh perspective on the biggest political stories. Not through opinions and anecdotes, but rigorous scholarship, massive data sets, and a deep knowledge of theory. If you want to understand the political science behind political headlines, then listen to Not Another Politics podcast, part of the award-winning University of Chicago podcast network.
Okay, so far we've been walking through how to predict rare weather events, but that ties indirectly to climate change, right? My understanding is that increasing greenhouse gases changes average global temperatures, which then does something that makes big weather events like fires or hurricanes worse or more frequent. And then the statistics also change?
Right, and this is where you tend to hear pushback with climate deniers saying you can't attribute things like Hurricane Harvey to climate change. I actually posed this question to Richard during our interview. There's lots of reporting that these rare events are becoming more common and linking that to climate change. But in statistical research, we often talk about how correlation is not causation. So how can you attribute some of this causation of these rare events to our changing climate?
Okay, that's a very good question. So let me just step back a bit and say a little bit more about the kind of analyses that people do. So one thing you can do, you can look for trends just in the observational data. So, for instance, one kind of analysis you can do, if we just go back to Hurricane Harvey for a moment. So Hurricane Harvey occurred in 2017. So a lot of people went back and said, well, let's look up to the data up to 2016. So we don't actually try to analyze Harvey itself, but just to say, well, on the data preceding that, is there evidence that the extreme events were getting more extreme? And the answer to that question is yes. A number of people have done analyses that showed that over that period, the records go back at least to about the 1950s. And over that time, the trends were certainly in the direction of increasing probabilities of extreme events. Now, that doesn't directly answer your causal question, because I could still be that there are other things going on that have nothing to do with climate change that address that. But in eventually what people come down to is comparing the results they get from the observational data with results that come out of climate models. So, let me just step back a bit and say what a climate model is. I mean, essentially a climate model is a computer program that simulates the climate and tries to show how climatic variables change under different kinds of forcing factors, which is the term used by climate scientists to refer to different things that can make the climate change.
But aren't there always going to be a bunch of naysayers asking how we can trust a model?
Yeah, I've heard folks be skeptical about models of climate change as well, asking questions like, how do we know to trust one model over the other? But actually, we can get a sense for how trustworthy these models are based on how well they've performed in the past.
Well, the fact is that climate models have performed remarkably well over the years. You can go back to the model predictions people were making 30 years ago and say, well, how have those actually worked out? And with the broad indicators like global mean temperature, they've done very well indeed.
So past is prologue, right? If the models have done a good job predicting weather events in the past, we should expect that they're modeling the true underlying changes and will also be quite accurate in the future.
Wait, but I still don't feel like we've fully explained how a climate model, which I assume is just spitting out data on like average temperatures, would then be able to tell us much about extreme weather events.
Yes. This is where we get into the field of research known as detection and attribution.
So detection and attribution is a technique. It was developed by climate scientists, and in fact the first paper on detection and attribution was by Klaus Hasselmann, who's a German atmospheric scientist who actually shared last year's Nobel Prize in physics, partly for that contribution. So when people talk of detection and attribution, detection is meant to indicate that we can actually observe the effect of greenhouse gases in the observational data. And then once you've got this detection, then the idea is attribution is trying to say, well, how much of the observed change can in fact be explained by greenhouse gases as opposed to other things going on in the world. But in the end, I mean, what the detection and attribution community has contributed, initially they were very cautious about it because back in the 90s, there was some genuine uncertainty about whether the observed trends were due to greenhouse gases. But over the years, as IPCC, the Intergovernmental Panel on Climate Change, they've come out with a whole series of reports, and the latest one was the 6th report, and each one has contained stronger statements about attribution than the previous one.
Okay, so detection is basically collecting data.
Yeah, like measuring temperatures and other weather phenomena around the world, as well as recording the amounts of greenhouse gases being released into our atmosphere.
And the attribution part is seeing how much of the changing temperature data is due to CO2 and such, rather than like other things.
Yeah, because it's not like burning fossil fuels has a one-to-one correlation with global temperatures. Things like volcanic eruptions or heavy logging, which then removes a buffer for carbon reabsorption, can actually really impact global weather patterns. We use detection and attribution to get a sense for what percentage of the climate change is being driven by all these different factors.
So essentially, it's a signal processing exercise where you take the signal that consists of the observed trend, meaning the trend in different places, and you can decompose that as a sum of individual trends plus an error. And there's still a substantial amount of error at the end of all that, but the coefficients of what is in effect a regression analysis, the coefficients of that regression analysis are what determine the attributions we're interested in.
Ooh, rewind. What's a regression analysis?
A regression analysis is basically a statistical method for estimating the relationship between one outcome and a bunch of other variables. Often you hear the outcome referred to as the dependent variable and the others as predictors or covariates, or coefficients, or independent variables. A regression just gives you a sense for how much that one outcome is dependent on each of those predictor variables that you plug in, as well as accounting for error or noise in the system.
Okay, I think I'm following, but maybe we need an example?
Sure, let's do that classic height example. So let's say we have the heights for a bunch of people and we want to know how much their height depends on a couple of factors, such as sex, childhood nutrition, family genetics.
So height would be the dependent variable because it depends on genetics, nutrition, and sex?
And those three factors you listed would be the predictor variables, so that when we run the regression analysis, we would essentially get a breakdown of how much height depends on each of those variables, plus an error term.
Okay, because it's not like height only depends on those three things.
You nailed it. Now, of course, regression analyses looking at global climate changes are just a smidge more complicated than our height example. But we also have just decades and decades of data that we can plug into the model.
We certainly have better measurements. I mean, we have bigger computers. The latest climate models run with much finer resolution than the climate models that were running 30 or 40 years ago. But I actually think the bigger difference is simply that we are now much further into it. 30 years ago, the trends that you could observe in the observational data at that time, you could certainly see trends, but they weren't anywhere near as strong as the trends we can see these days.
So better computers processing more years of collected data means we're pretty certain that our climate models are accurate.
Yeah, for better or worse, we've gotten better at predicting the frequency of bad storms and rising global temperatures because we have so many decades of experience with it.
Oh boy. Okay, so now that we have all this data feeding into these models, can we put it to use? Like specifically, how far away from the coast should I be buying my future beachfront property? Except I the idea of me buying a home is ridiculous.
I know. That's why I originally asked Richard where I should live to avoid the brunt of the effects of climate change. But while we have a really great sense for how the planet's systems are changing on the large scale, it gets harder to predict the more that we zoom in.
With the observational data, you can actually get down to very fine spatial levels because we have a number of different sources of observational data. We have the weather stations, of which there are already several thousand across the United States, but then those can be supplemented with radar measurements like LIDAR and with remote sensing data from satellites. So people can get down to very fine level resolution with the observational data. But the climate model data doesn't work at that level. Even the best climate models, the resolution is of the order of maybe 25 or 50 kilometers, which is not enough to see very fine level effects. But these large scale attribution problems, saying how much can you attribute specifically to greenhouse gases as against one of the other possible contributors, those questions are a bit harder to analyze at the very fine detailed level, though people are still trying and still able to do it on a finer spatial scale than they were several decades ago.
So what you're saying is that he can't tell me exactly where I should live to avoid a tornado, so maybe we should just do something about climate change?
Ooh, what a novel idea. But yeah, as is true with so many fields of research, it comes down to an issue of scale. When you're looking at a smaller area, you start to have to take into consideration all sorts of those local factors.
So even though climate models can tell us how Lake Michigan is going to change in the next decades, the models aren't looking at this on a specific neighborhood by neighborhood basis.
Not yet, at least.
Okay, but before we wrap, I want to bring up a topic you sort of started the episode with.
Ooh, are we going to talk about Texas again? You know I have so many opinions.
Yes, but I specifically want to bring up the winter storm you talked about. I mean, we use climate change and global warming pretty interchangeably, but that was a winter storm, not a heat wave.
No, you're totally right. And this is the point that climate deniers bring up pretty often. How can an extreme winter freeze be due to global warming? The answer is basically that how the ocean's currents and air circulation and other global phenomena interact are all pretty complex.
So, and another thing people say is why do you get it more extreme cold events when the world is supposed to be warming up? But the fact is that you have these non-linear effects that mean that some parts of the world are warming up, but other parts actually can be getting cooler for exactly the reason you said, where or not necessarily getting cooler overall, but a higher frequency of extreme cold events in winter. And we've been seeing that in the southeast as well.
So it's not just the same consistent warming everywhere.
No, it's more like all these different systems are changing how they interact, and we're seeing more extreme climate events of all sorts. Sadly, I think talking about the nonlinear effects of climate change is going to have to be saved for another episode of Carry the Two.
Okay, I'm glad to know this won't be our only climate change episode because I have a lot more questions.
Oh, it absolutely won't be our last. MC has 6 core scientific themes, and one of them is climate science, so we will definitely be revisiting this topic again soon.
Actually, didn't you mention something about a long program at MC?
Yes, MC's fall programming from mid-September through early December is centered around confronting global climate change. I'm really excited to see the finalized titles for all the talks.
Oh, cool. I'm sure that we'll have a lot more material to work with then.
As always, don't forget to check out our show notes in the podcast description for more on Richard's work and further resources on mathematics and statistics behind climate change.
And if you like the show, give us a review on Apple Podcasts or Spotify or wherever you listen. By rating and reviewing the show, you really help us spread the word about Carry the Two so that other listeners can discover us.
And for more on the math research being shared at MC, be sure to check us out online at our homepage, mc.institute. We're also on Twitter at MC_institute, as well as Instagram at mc.institute. That's MC spelled IMSI. Our 2022 fall-long program, titled Confronting Global Climate Change, will include some fantastic workshops on this topic, so you won't want to miss that.
And do you have a burning math question? Maybe you have an idea for a story on how mathematics and statistics connect with the world around us. Send us an email with your idea.
You can send your feedback, ideas, and more to sadiewit@imc.institute. That's SADIEWIT@imsi.institute.
We'd also like to thank our audio engineer, Tyler Damme, for his production on the show. And music is from Blue Dot Sessions.
Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We're supported by the National Science Foundation and the University of Chicago. This is where we get to Ian's specialty, coughing on mic.
Girl, I'm coughing at my elbow like Obama taught me.
I hope you like elote because I'm very corny. Oh, did I tell you? So I'm just like, all I want is a Western moment, and every single one has been ruined for me.